Good afternoon, students.
Good afternoon, sir.
Good afternoon, sir.
Thank you. Today we will get into the fourth unit of our machine learning subject, and I hope that you are continuously following all the materials which I have already uploaded in the Google Classroom, right? Even if you have not done that so far, kindly go through that whenever you find some time, so that the subsequent topics which we are going to learn are more dependent on the previous introductory classes, right? Or at least to get a good knowledge and information on machine learning, all those basic topics will be much more useful, right? So at the end of the semester, normally we have 45 hours, and for each hour I have prepared some 10 slide PowerPoint presentation. So if you put together 45 hours, at least 45 into 10, 450 PowerPoint slides you will have. Right? If you make it as in the form of a book with a cyclostyle or some spiral binding, I'm very sure that will be very much useful for you till you go to your further stage in this specific topic. So don't take it for granted. Make use of those technical informations. Now we will go into the fourth unit. Is my screen visible?
Yes, sir.
So your fourth unit talks about another specific machine learning approach, right? The third unit talks about decision trees and how decision trees were used for regression application, right? Regression applications, mostly our linear method comes under the category of regression applications. And we saw a bit on logistic regression, which also is used for classification applications, right? So decision tree can be used for both regression and classification applications. We saw that predominantly from a regression point of view in the third unit. Now we go into the next algorithm or method, which we are going to call it as support vector machine. So there are many machine learning approaches, but the basic principle remains the same. If it is supervised, you need to train it with the past history of data and a target vector. But if you go for an unsupervised, there will not be any target vector. An iterative approach by which some parameters will be adjusted. Once the parameters are finalized, you can go for the testing process to either go for finding a number or finding a class or a category. So now we will see about support vector machine, and in this class I am going to give you some basic introduction about SVM, and we do not go into the mathematical part today. Try to grasp the theoretical information or background details of this support vector machine. Support vector machine is another simple algorithm that every machine learning expert should know. Right? SVM, right? Support vector machine is also called as SVM. If you have searched for your project or something like that, you would have come across this specific word called as support vector machine. It is highly preferred by many of the machine learning engineers as it produces significant accuracy with less computation. Right? The accuracy seems to be a bit high in comparison to our decision trees, and at the same time, the computational power, or we can say the number of mathematical equations or the complex stuffs in your SVM is less. When I say less, it is not zero. In comparison to your decision trees, you can say it is a bit better. Support vector machine is abbreviated as SVM, and again, like our decision trees, it can be used for both regression and classification tasks, but it is widely used for classification applications. Right? Whereas your decision tree, we give more importance to regression. Of course, you can also use it for your classification, but from our content point of view, we gave much importance towards the regression part. But in support vector machine, again can be used for regression and classification, and we are going to give much importance from a classification perception. So now we'll see what is support vector machine. So the objective So the main purpose of the support vector machine is to find a hyperplane, right? It's to find a hyperplane in an n-dimensional space. So here we have two technical keywords which you should understand what is meant by a hyperplane and what is an n-dimensional space, right? And this n-dimensional space is used for classifying the data points. Say, for example, you take a graph, normal graph, you use it for the regular labs. You will take an x-axis and an y-axis. In that case, the number of features we have used is 2 because we have 2 axes. Or we can say that the number of features is equivalent to the number of dimensions of the space. So a graph is a 2-dimensional object. We also have a 3D space. We also have a 4D space. We also have a 5D space, right? So whenever you say, I'm going to have something on a space or a spatial domain or a dimensional structure, it is based on how many axes you are going to have. In a normal graph, you'll have x-axis and y-axis, or we can call it as a 2-dimensional space where n is equal to 2, or this n corresponds to the number of features, right? Now in that graph sheet, what you are going to do is you are going to draw a hyperplane. A hyperplane is one or a structure which is always 1 dimension less than your total dimensions. Say, for example, you can look at these diagrams, right? You can look at this diagram. Now here, how many features I have? 2 features, because x1 is 1 feature. Don't worry about whether it is input or output. We have an input feature as x1 and maybe an output feature as x2, or you can say a set of points. To draw a circle and a square, I need a x coordinate and a y coordinate. So here it is going to be a 2-dimensional space. Now when I say 2-dimensional space, my hypothesis is, or the hyperplane will be always in the form of a line, right? When I say line, you are going to draw in a single linear fashion. In the same way, you can also have a 3-dimensional space. The second diagram shows the R square is a 2-dimensional space where you have a hyperplane. Hyperplane is 1 dimension less than. That means a single dimension or a single line. But when you look at your R3 structure, the third diagram, you can see the number of axes is 3. You have x-axis, you have y-axis, and also you have z-axis. If the number of axes is 3, then the hypothesis or the hyperplane should be 1 less than the total features or the total dimension. So it will become a 2D structure or a rectangular or a square region. This is called as hyperplane. Yes, line is also a hypothesis. A square or a rectangle is also hypothesis, but depends upon the number of dimensions, the nature of your hyperplane varies. In all the previous classes which we saw, I explained you with the help of only a 2-dimensional space. That's why we talked only about a line. Right? A line is a single dimensional object. But when you go for a higher dimensional objects, then we need to go for a rectangle or a square hypothesis. So what is the purpose of these hyperplanes? They are decision boundaries that help classify the data points. Right? So try to find out all the data which are on one side of the line and try to find out all the data which are on the other side of the line. So whenever you have a testing data, try to find out whether it is above the line or below the line. Then you can put that data into that specific category. This is the process of your classification. In the previous class also, or in the previous sessions also, we saw about regression, where again we had a line, but we did not went for, or we did not attempted to divide the data. We just had an intention to find out whether your line exactly matches with all the points. So my individual data point will give me the correct answer. But here it is not the case, because we are going to talk from a classification perception. So these are decision boundaries that help classify the data points. And data points falling on either side of the hyperplane can be attributed to different classes. So your duty, again, similar to decision trees, in support vector machine is also to find the hyperplane. But now the process is slightly different. try to find out how many data are on one side of the hyperplane and how many data are on other side of the hyperplane. And as I told you, the dimension of the hyperplane depends upon the number of features. If the number of input feature is 2, then the hyperplane is just a line. That means the hyperplane is always one dimension less than the overall dimension of the system. That we call it as hyperplane. If it is a plane, the number of features and the number of hypotheses are going to be same. But when we say hyperplane, it is one less than the original dimension. If the number of input feature is 3, then the hyperplane becomes a 2-dimensional plane. It becomes very difficult to imagine when the number of features exceeds 3. So when you have a 4-dimension, 5-dimension, 6-dimension object, the way in which you are going to have a hypothesis becomes complex. You cannot just say it is a 2D object. It is going to be a 3D one. Say, for example, 4 features. Then your hyperplane or your hypothesis, the decision boundary itself should be a 3D object, which is going to be much more complex. But what we are going to learn is from a basic perception that maybe having a 2 features, or to some extent we will learn about something with 3 features. And this is what a decision boundary is all about. Now you can see 2 features are there, and the green color lines, they are hypotheses. They are hypotheses. And in this diagram, 1, 2, 3, you can find 5 lines. Right? All the 5 lines, the beauty is all the 5 lines are able to classify circles under one category and squares under another category. But the final answer is only one hyperplane or only one hypothesis. So the question is, what should be the correct line? So that whenever I have a testing data, it will correctly fall under either circle category or square category. Right? But the confusion is how to choose the best hypothesis or hyperplane. So this is an example for a higher dimension hyperplane, which we just saw. So to separate the 2 classes of data points, there are many possible hyperplanes that could be chosen. Even you can try in your note, you can draw many objects, 2 different types of objects, and different lines at different angles can be drawn. Now our objective is to find the plane that has the maximum margin. In our previous decision tree concept, we tried to find out that our line should touch all the data points. That is regression. Right? But here I am going to divide my circles and squares as per our previous diagram. So I want to find the plane that has the maximum margin. What is the maximum margin? The maximum distance between the data points of both the classes. Right? So when you have a diagram, like this, right? I want to have a line which will be dividing my square and circle with a larger distance. That means the circles and squares are very far apart. That means there is a good difference. That's a good difference between my circles and squares. So whenever I go for testing, there will be a good chance that it will fall under circle or it will fall under square. Suppose on the other case, contrary to what I have told, if there is a circle and a square very close to each other, if the distance is very small, that means whenever I have a testing data, there may be a confusion whether it belongs to circle or square. So here our process or purpose of choosing the hypothesis is based on the margin. It is based on the maximum distance between the data points of both the classes. So maximizing the margin distance provides some reinforcement so that future data points can be classified with more confidence. That's why we say square and circle should be far apart. If they are far apart, it will be easy for you to classify any testing data. Right? Now it is this here we have a classical illustration for the margin. Right? Theoretically, I told you we need to have a maximum distance. How will you visualize that? So when you go for visualization, right, try to take the points which are very close to each other first. Right? In the square, we have 5 squares. In the circles, again, we have 5 circles. Don't go for finding the distance between the farthest circle and the square. Try to find out the triangle, square and circle which is nearby. Right? So in this square class category, we can find that 2 squares are nearby. right? In the circle category, we have one circle nearby. So the distance between that circle, not all the other circles, you leave out all those things. That circle which is near to that specific squares, or the squares which are near to the specific circles, that distance should be as much as possible. If you consider the other circles and squares, definitely their distance is going to be far from the diagram itself. But we have to make sure that the closest possible squares and circles itself should have a sufficiently a longer or a higher distance. Right? So that will be the best hyperplane. That will be the best line which we can classify our squares and circles with. Right? Here I have given a difference for you between for a small margin and a large margin. Right? So in the first diagram, you can see that the width, right, the distance between your square and your circle. When I say square and circle, the square and circle which are close to each other, right? The circle which is very close to each other is one, and the square is also on the other side. You have one. But when you see that the hyperplane is formed in such a way that the margin is very less, the margin is very less between the square and circle. But when you look at the other diagram, on the other hand side diagram, you can find that the margin is bit more. So these data points, classification of the second set of data point is much more better, much more easier, much more accurate than going for the first diagram. So that is called as margin. So the point here you need to note down is, when I say the distance, it is not between all the squares and circles. It is between the circles which are close to in their specific category and the squares which are close in their specific category. That distance should be as much as possible. Maximizing the distance between these two is the ultimate objective of support vector machine. Right? So SVM is all about margin, but when you talk about decision tree, it is all about the two parameters B0 and B1. If you can correctly find out B0 and B1, you fix in the line and you can predict the data regression. But when you go for SVM, if you can try to find out the hyperplane based on the margin, whichever is giving the maximum margin, you choose that hyperplane and then you go for the classification. Definitely you are going to get a good amount of accuracy. Right? So in this diagram, we say that the circles or the points, the data points, which are close proximity, which are in close proximity, are called as support vectors. Right? Support vectors. You can see that in the green color circle category, the circles, two circles, there are only two circles which are close to the, or which are standing in front. We can say standing in front. Those are called the support vectors. In the square, we can see another three things which are standing in front. So here we have 5 data points which we are going to call it as support vectors. So our entire story revolves around these 5 support vectors. That's why this method is called as support vector machine. They are supporting us to find out the best margin and the best hyperplane, not all the data points. You may have plenty of data points, but the points which are close to each other, in the sense that which are nearby, right, which are standing in front, they are going to be called as support vectors, and they are useful in making a correct decision of how much the margin is and where I should draw the line. So support vectors are data points that are closer to the hyperplane, that is the decision boundary, and influence the position and orientation of the hyperplane. Suppose if the data points or the support vectors are sufficiently far apart, then your hyperplane decision boundary will be large, your margin will be large. But if the data points are located in such a way when both are close, then the hyperplane will have some difficulty in forming the clear differentiation between these two categories. So they are going to influence the position and the orientation. Right? Now in this previous diagram, you can see both are sufficiently like that, you are drawing a line. But if they are on a different angle, then the way in which you have to form the line will be different, maybe a diagonal or something like that. So the orientation and the position is determined by these support vectors. So your duty is try to find the best support vector. Based on the support vector, find out the margin. Based on the margin, you find out the best hyperplane. Then you will go for classification. Almost 60 to 70%, same as that of our decision trees, but the application is for classification. Using the support vectors, we maximize the margin of the classifier. Deleting the support vectors will change the position of the hyperplane. Right? Sometimes when we draw the graph, we draw a graph and all the points may not be properly under one cluster. So what we do is we sometimes will remove some data points. Maybe if you have drawn the Smith chart for the antenna, maybe figure of 8, some graphical structure is there. I'm not sure whether you have done that in your antenna and wave propagation classes. When you draw that graph, normally we miss out some data points. But if that data point is a support vector, how do we say it is support vector? If it is close to the hyperplane and if you delete that, then you may end up with the wrong hyperplane, because those things are going to play a crucial role in developing our SVM. Now, this is the basic concept of SVM. Now, using this concept, how we are going to use the classification process, how we are making use of SVM for the classification procedure. In logistic regression, as we saw in the previous session, we first go for a linear regression. You will get a predicted output, and then we pass it through a function called a sigmoidal function, whose range is between 0 to 1. Right? And we say that if 0, right, or if it is 0.5, it crosses 0.5 as a threshold value, we put it to one class, and other times we put it in another class. This is called as logistic regression, which is somewhat used for classification applications, right? But you can see that the range between 0 to 1 is very, very less, or the margin is very, very less. What will you do when you get a value of 0.52? 0.52. Will you say that 0.52 is greater than 0.5, or will you say that it can be put under another category? Because your range is small, there is a high chance your data points or your predicted output may fall under the same category, which may lead to a wrong result. That's why I did not advise you to go for logistic regression. How do we solve that in SVM? In SVM also same procedure, same hyperplane, same, everything is same, right? But here the only difference is the range is between 1 to -1, right? Sigmoid gives only 0 to 1. But in SVM, we are making use of some other process, some other function to have a range between 1 to -1. So the difference or the margin is almost doubled in comparison with your logistic regression. So better margin, a larger margin, and the chances of your accuracy being high is also good. Right? That's the difference between logistic regression and support vector emission. So now we will see quickly see some different scenarios of classification, so you can understand it in a better way. First scenario, right? This is the diagram, or this is the structure of the data points. You cannot do anything with the data points. You need to just plot based on your X and Y. You need to plot the data points. So say, for example, you have some data points like this. The red color are all on the one side and blue color stars are on another side. Now we can see that there are many ways, or at least 3 ways in which you can divide this, right? Randomly, we have formed some hyperplanes, but my duty is I need to classify the star and circle. Now, can you tell me which will be the correct hyperplane which I should use from this diagram? Can anyone unmute your mic and tell me whether it is A or B or C? Which line or which hyperplane will give me the correct classification of circles and stars?
B.
B. Very good. B is the one. Very easy. This is very easy because straight away we know that your star cannot mix with the circles. That is a thumb rule, right? Select the hyperplane which segregates the 2 classes better. So in this scenario, hyperplane B has excellently performed this job. If you choose A, there is a high chance that you have some circles also with stars. If you choose C, again the same thing. Now we will go into the scenario number 2. You have some data points like this, right? Data points like this. Here we have 3 hyperplanes, and interestingly, all the 3 hyperplanes are able to classify them properly. In the previous case, the student who gave the answer, it is very easy for him because he just saw that only option is B. But here I have three options. Now, how can we identify the right hyperplane? Now, can someone else give me the answer? You have three options, A, B, C. All the three gives the correct answer. Right? But only one hyperplane is the correct one. Can anyone tell me?
C.
C. Excellent. C is the correct answer. Can you tell me why C?
Maximum margin.
Maximum margin. The distance between the stars and the circle is more. If you look at the star, it is very close to B. Right? The support vector, the star which is near to the hyperplane, it is very close to B. When you look at your circles, it is close to A. But when you look at C, it is at a sufficiently larger distance for these two things. Right? Now we are doing, or we are going one step above from the scenario one, that we are trying to choose something which has a maximum margin or the distance between the nearest data point on either class, not one class, on either class, and the answer will be your C. Option, the thing is C. This diagram shows the distance, right, from the star and also from the circles. Right? So this is scenario number 2. So when you choose an SVM, make sure that whether your conditions fall under first category or second category or the categories which I am going to discuss with you. So above you can see that the margin for hyperplane C is high as compared to both A and B. Hence we name the right hyperplane as C. If we select a hyperplane having low margin, then there is a high chance of misclassification. Say for example, if I choose A, because star is very close, there is a high chance the star may spill over to the circle category. Circle category may get a correct classification accuracy, that is fine. But when you go for star, star may spill over because the boundary is very, very thin. In the same way, if I choose A, it is closer to circles, so the circle category data may face a misclassification rate. That's why we say both the classes should have a broader margin or a higher margin from the line. So now we'll go to the third one. Now which one you will choose? Right? Now which one you will choose? If you take A, right? If you take A, it is able to classify your stars and circles correctly, but the margin is very less. If you take B, right? If you take B, again, it is going to divide or classify your stars and circles with a better maybe accuracy. Maybe one star you may lose out, but the margin is more. Which one should you choose? Whether you should give preference to the margin or whether you should give to the accuracy. Any guess? Any guess? A or B? I'll repeat once again. A, if you look at the line A, it is able to classify stars and your circles in a better way, right? There is no chance of misclassification, but the line is very close to the circle and the star support vector. But if you take B, the margin is sufficient, but you need to lose one star, maybe one data, inaccurate data may be there. So what we are going to choose? Right? Some of you may have selected the hyperplane B, stating that my accuracy is good, right? Even though it has a higher margin compared to A. But the idea of support vector machine is selects the hyperplane which classifies the classes accurately prior to maximum margin. Right? Here, hyperplane B has a classification error and A has classified all correctly. So whenever we say margin, but still the first preference should be given to the one which is giving you 100% training accuracy. 100% training accuracy. In that case, your A is going to be better than B, even though B has a good margin. In our scenario 2, we talked about only the margin. If you have the same mindset, when you come to scenario 3, you may think that maybe I am going to lose only one star. That's fine. But let me go for hyperplane with a higher margin. No. support vector machine should give more importance to accuracy, and the second priority is your margin. So here our option will be your A. Even though B is better, B is having a better margin, the classification accuracy is slightly low because we have 1 star coming into the another category. Now we go for scenario 4. So scenario 3 is actually a mixture of scenario 1 and 2. Right? Now we go for scenario 4. What is scenario 4? Right? Scenario 4, you have some data like this. In the previous case, with the line, you can miss 1 star or misclassify that and put it in another category. But here what happens? I am unable to segregate the 2 classes using a straight line, as one of the stars lies in the territory of other circle. Right? The previous case, the star is closer to our star. Even though it is in the circles category, it is a bit closer to the star. But here what happens? It is completely on the other side of the circle. Right? This we are going to call it as outlier. In machine learning language, we do not call it as noise. All the noises which we come across our communication or any other topics in machine learning, we are going to call it as outliers. So how I'm going to do that? Right? 1 star at the other end is like an outline for star class. So SVM algorithm has a specific characteristic features to ignore outliers. Right? That means it will not take that star into account. Whenever it sees star at some other category which is completely mixed with other circle, we are not going to take it as a data point, but we are going to take it as a noise or an outlier. Right? And we are going to simply ignore the star. We are going to simply ignore the star, which is in the category of the circles. Right? It should not be treated as a data point, but it should be treated as a noise, a wrong measurement. When you take a measurement, say for example, in the Smith chart, when you draw a Smith chart in the antenna experiment, you will take points at different angles. Sometimes you unknowingly you would have repeated for the same angle, or some internal noises may be there. Right? Because of that, you would have got some points like this. So these points should be taken as noises, and that will be automatically taken care of by your SVM algorithm. No need to worry about the star, just go by your normal method. Scenario number 5. You may have some data points like this, extremely complex. How can you solve this? How can you classify this? It is not possible with the data points which we have. So what we are going to do is, we are going to have or rearrange this data in a different way. Right? So before going into SVM or the initial part of SVM, we can add some structures in such a way that the data which are arranged in the circles or a circular fashion can be put in a linear fashion too. Your SVM has that capability also. Right? By adding some new features, you can pull that points in a straight line or some direction in such a way that it can be easily classified with a single line, because it is going to be only 2 features, circles and stars, are X and Y. So you should have only a line. Hyperplane should be only a line. You cannot have a diagram or a square or a rectangle. So you need to rearrange your data points, then you go for it. So these are different cases which you may encounter when you go for finding the hyperplane. But make sure that accuracy is the first important thing that should be given higher priority. Then comes your margin. And based on this margin and based on the distance, we are going to have some mathematical equations, mathematical formulas by which we can convert all the theoretical contents into your model. That model can be used for finding the best margin and thereby going for classification. We will see the mathematical concepts another day. If you have understood the concept, and not only understanding SVM, you must be able to correlate to find the difference between your decision tree and SVM. Both almost look the same. You have only hyperplane to classify, that hyperplane to fix all the points. But what difference that you need to identify, how SVM is different from decision tree, that is also very, very. So advantages, it works really well with a clear margin of separation, right? So the accuracy is going to be always high, because always we are going to focus on the maximum distance. It is effective in high dimensional spaces, right? So when you have a more number of features, your SVM is going to be much more effective. Or we can say when the number of dimension is greater than the number of samples, right? Two features. In the previous case, I have in a diagram like this, I have two features, but the number of samples, when I say number of samples, the number of circles and star, I have 3, 6, 8, 10, 13, 16, some 20 samples I have. Two features and 20 samples. So the third point says it is effective in cases when the number of dimension is greater than the number of samples. Right? So more importance is given to the dimensions rather than going for the number of samples. If the number of samples becomes too high, if the data becomes too high, then your SVM also will have some problem in classification. That's why we go for another technique called as artificial neural networks. And it uses a subset of training points, so it is memory efficient. As we saw that only the support vectors are used for determining the distance or the margin. So instead of going for all the data points, we can choose only that minimal data points and then we go for processing. So it is enough to store, give importance to that data points. That's why we say it is memory efficient. We have also some drawbacks. It doesn't perform well when we have large data set. That's what I told you in the previous point. Right? Large data set means more number of samples. When you have more number of samples, the pictorial representation, visualization in the graph itself will become complex. They may have outliers. They may have a completely random data set, and your SVM will not be able to properly divide that because our SVM is based only on distance. When you have a data set in such a way that the distance can be enlarged and then go for classification, it's fine. But when we have a mixture of chaotic data, it may not be able to do that. When we have a large data set, there is a high chance you may get a chaotic data. For that, we go for artificial neural networks. Because drawing a line is very difficult and the training time also will be much more high. It also doesn't perform very well when the data set has more noise. As I told you, one outlier can be removed, but if more and more data are available on the other end, then you cannot treat all those data points as noise. Right? So in that case, again, your support vector machine fails. And they doesn't directly provide probability estimates. Right? Normally in a logistic regression, we saw that when you give it to a function, it gives in 0 to 1. Right? But in SVM, you cannot get a direct probability estimate. We have a procedure. These are calculated using an expensive 5-fold cross-validation. 5 times you need to run the program. We saw about cross-validation, having the training samples again and again, misjuggling it. Right? With the advancement of software languages like Python, we have the process inbuilt within that. But algorithm-wise, if you look at that, that is going to be huge or heavily computationally complex. That also is one of the drawbacks of support machine. But now with the advancement of machine learning, people are running towards artificial neural networks and deep learning. Nevertheless, decision trees, support vector machines, and few other machine learning techniques are also useful when you have a very simple application or your application matches with the PROS criteria. Then you can make use of SVM. So next class, we will go into the mathematical concepts of it. Let me mark the attendance quickly. Amulya, Judson,
Sir.
Samyukta, Angel, Angel absent, Ajit Pawan,
Present, sir.
Abhinaya,
Yes.
Kiran Kumar,
Present, sir. Present, sir.
Manideep,
Present, sir.
Bhanu Teja,
Yes, sir.
Jennifer, Priyadarshini,
Yes, sir.
Jeevan,
Present, sir.
Afreed,
Present, sir.
Jayant,
Present, sir.
Vikas,
Present, sir.
Alfini,
Present, sir.
Bhuvaneshwar,
Present, sir.
Sumant Kumar,
Present, sir.
Ramesh Kumar,
Present, sir.
Neeraj Kumar,
Present, sir.
Zubair,
Present, sir.
Kirti,
Yes, sir.
Dinesh,
Yes, sir.
Tejaswant,
Yes, sir.
Chandana Priya,
Present, sir.
Karthik,
Yes, sir.
Vijay Kumar,
Yes, sir.
Yes, sir.
Roman,
Yes, sir.
Janish,
Present, sir.
Rex Vimal,
Yes, sir.
Harshavardhan,
Yes, sir.
Uday,
Yes, sir.
Sakib, Sakib absent, Siddharth,
Yes, sir.
Praneeth,
Yes, sir.
Salomi,
Yes, sir.
Livingston,
Yes, sir.
Alan,
Yes, sir.
Ronan, Ronan absent, Sai Kiran,
Yes, sir.
Ronan kept in chat box, sir.
Ronan chat box, Joshiba,
Yes, sir.
Shiny,
Yes, sir.
Jasmine,
Yes, sir.
Kavya,
So she's having some network issue.
who Kavya?
Yes, sir. She
Okay.
left at 12:40.
Okay. Jay Surya. Okay. Joanna Paul,
Yes, sir.
Manasa,
Yes, sir.
Ashrita,
Yes, sir.
Narasimha Reddy,
Yes, sir.
Puneet Kumar,
Yes, sir.
Shiny, Joshua,
Yes, sir.
Nagakiran,
Yes, sir.
Suraj,
Yes, sir.
Monica,
Yes, sir.
Taufik,
Yes, sir.
Manideep,
Present, sir.
Dikshit,
Present, sir.
Maria Angel,
Yes, sir.
Amrut,
Yes, sir.
Pavan Kalyan,
Yes, sir.
Sainath,
Present, sir.
Gautam,
Present, sir.
Jagat Chandra,
Present, sir.
Vivekananda,
Yes, sir.
Shashank, Sai
Chat
Ganesh.
box.
Okay. Sai Ganesh,
Yes, sir.
Gopi Chand,
Present, sir.
Ritvik,
Yes, sir.
Solomon,
Yes, sir.
Sudarshan,
Yes, sir.
Sujit Kumar,
Present, sir.
Suresh
Sudarshan,
Kumar.
present, sir.
Okay, Suresh
Yes,
Kumar,
sir. Yes, sir.
Sunny,
Present, sir.
Amrita Das. Okay. So absent is number 3 and number 46. Okay, thank you, Pa. You can leave the Google Meet.
Sir, Suresh, present, sir.